So we're going to close out thermochemistry today, and we're going to do it by talking about the most common technique in thermochemistry, the technique that you did 2 labs on this week, and that is calorimetry. Now, as we've kind of uncovered this week, enthalpy is not an easy thing to measure directly. Experimentally, it's kind of hard to trap heat because generally speaking, unless we've got an isolated system, heat is going to be able to transfer in and out of our objects. Now, the technique that is used to do this kind of transfer is that of calorimetry. Calorimetry is kind of the best tool that we have for this particular job. And the apparatus that we use for this technique is the calorimeter. And again, you've seen some of this because we've already done some experimental work with calorimeters and calorimetry in lab. But now we can kind of formalize it. Calorimetry uses heat capacity, specific heat, as a means to calculate that transfer. So those transfers of energy get directly related to heat capacity calorimetry. And as we have seen, and this is just more for review purposes than anything else, there are multiple ways of measuring heat capacity. One of them based on a per molar kind of measurement, the molar heat capacity, and one that is measured on a per gram basis, the specific heat. Now, generally speaking, we tend to focus more on the specific heat just because it's a heck of a lot easier to measure. It's a lot easier to measure the mass of something, or as we did, the volume of something and then apply the density. It's a lot easier to go in that world than to be constantly converting grams into moles. And so what we come to are questions like this. This is a kind of question that we can answer using a calorimeter and the technique of calorimetry. Now, the equation that comes into play with this is the equation that we explored yesterday. Q is equal to M times C times delta T. Where if I look at the heat being transferred in or out of a substance, I can measure that heat by taking the mass of that substance, multiplying it by the specific heat of that substance, and by the temperature change that that substance experiences. Now, what we have here is a heat transfer kind of problem. Let's say that we have 237 grams, 1 cup of hot brewed tea, hot being 100 Celsius, so really hot, in an insulated mug that we add 250 grams of ice to. That ice being initially at negative 18 Celsius. If all of the ice melts, what will be the temperature of the tea? And we can assume that the tea has the same thermal properties as water. So what we have here are 2 basically opposing phenomena. We've got the ice that is going to go through a process of warming, plus a process of melting, and then presumably another warming phase to get up to the thermal equilibrium with the water. And on the opposing side, we have the T that is going to go through a cooling process. But that's the only process that it's going to undergo, presumably. Now, this is a heat transfer. We know that the heat is going to transfer from the T to the ice. And assuming that because this is an insulated mug, assuming that the insulated mug is going to act as an isolated system, we're not going to experience any heat loss to the surroundings. All of the heat that goes from the T to the ice should happen ideally, perfectly, 100% transfer. So with that being said, the heat loss experienced by the T would have to be equal yet opposite of the heat gained by the ice as it goes through its transformations. So now we just need to figure out how much heat are we talking about here? Because the heat of the ice is a series of processes. We have to have the heat of the ice warming plus the heat of the ice melting plus the heat of the now melted ice, so we'll call that water, warming. All three of those processes are all happening. And that's going to be equal to the opposite of the heat for the T. So we're going to need a calculator for this process. And I left mine in the lab, so I'm going to go over there real quick. So when it comes to these processes here, we know that we have equations for each of them. So for the ice, it would be its mass, 250 grams, times the specific heat of ice, which we're going to have to go back a couple of slides and get that. So that would be 2.11 joules per gram degree Celsius. And the change in temperature, it's going from -18 up to the freezing point. So that's 0 minus -18 degrees Celsius. For the ice melting, remember that one is N times delta H of fusion. So we gotta again go back. And the molar heat of fusion is 6.01 kilojoules per mole. So 250 grams of ice, 250 divided by 18.02 grams per mole is 13.9 moles. Times 6.02 kilojoules per mole. And then for the water, heating up 250 grams. Specific heat of water is 4.18 joules per gram degree Celsius. And we don't know the final temperature, but we know the initial temperature was 0. So on this side of the calculation, we're starting to get an idea of how much things have kind of changed. So if we start doing some of the calculations, 250 times 2.11 times 18 would give us to 3 significant figures. 9,500 joules. 13.9 times 6.02 will give us 83.7 kilojoules. $250 times 4.18 will give us 1,045 joules per Celsius times TF minus 0. Now, the reason I did that particular calculation is going to become apparent once we kind of start combining things. So if we move all of this to a whiteboard here, we've got 9,500 joules plus 83.7 kilojoules plus 1,045 joules per Celsius times the final temperature minus 0. And this is all going to equal, remember, we've got still the other side of this equation, the opposite of QT, which would be 237 grams times 4.184 joules per gram degree Celsius, because we're told that the T has the same thermal properties as water, multiplied by whatever the final temperature is minus the starting temperature, 100 Celsius. So we've got to combine these two energy terms together. We've got to combine these two terms together as well. For argument's sake here, we're going to turn everything into joules just so that we don't have to convert all of our, it's easier to convert 1 kilojoules into joules than 4 joules into kilojoules. So $9,500 joules plus 83,700 joules. We've got 93,200 joules. And I'm going to go ahead and expand this. 1045 joules per degree Celsius times TF minus 0 is equal to negative 237 times 4.184 is negative 992 joules per degree Celsius times TF minus 100 degrees Celsius. So 93,200 joules plus 1,045 joules per degree Celsius times TF is equal to negative 992 joules per Celsius TF. Thank you. Plus 99,200 joules. And that's coming from the negative 992 multiplied by the negative 100. The degrees Celsiuses cancel out. So problems like this, these ones stink. There's a lot going on in them. You've got a lot of algebra. And in this particular case, usually they're not this bad. Usually we start with water in the same phase. Yeah, everything's in the same phase. So we're going to have to deal with a phase change on top of something else. All right, we're going to combine like terms. So I'm going to subtract 93,200 joules from each side. So that's going to give me 1,045 joules per degree Celsius is equal to 6,000 joules times negative 992 joules per degree Celsius times TF, or excuse me, plus. And now I'm going to add the 992 to each side. So 1045 plus 992, 2,037 joules per degree Celsius times TF is equal to 6,000 joules. I do the division. TF is equal to 6,000 divided by 2,037. I get to three significant figures, 2.95 degrees Celsius. So in the end, temperature of that tea got pretty cold. Now, like I said, this is a long process. These kinds of heat transfer problems are long. What we have to kind of just remind ourselves of, get ourselves into the framework of thinking, is that it is a transfer process. So whatever happens to the one thing, the exact opposite is happening to the other. Very similarly to what we did in our calorimetry experiments in lab. The thing that we measured for the water was the opposite of what happened in the reaction. They were equal yet opposite. The reason this one is particularly difficult is because the heat transfer had to occur in stages. So it was like taking a heating curve problem and slapping it into a calorimetry problem. It had multiple phases on it. And that's why this problem was particularly difficult by comparison. So any questions with this problem before we do some hopefully easier examples of calorimetry? Okay, so this one should be a little bit more familiar. When 200 milliliters or 0.2 liters of 0.2 molar hydrochloric acid is mixed with 0.2 liters of 0.2 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the mixture increases from 22.15 to 23.48 degrees Celsius. If the two densities are 1.00 grams per milliliter, what is the value of delta H? So there are a couple of things that are going on here. We got to make sure that we kind of put our brains around all of them. So first of all, we know that Q is equal to M times C times delta T. Now our mass here is going to be the 200 milliliters of the acid plus the 200 milliliters of the base. So a total of 400 milliliters of solution times 1 gram per milliliter would be 400 grams. So our mass of the total solution is 400 grams. The specific heat, we're going to assume that this, like most aqueous solutions, is close enough to water's values that we can kind of just assume. So we're going to put in here 4.18 joules per gram degrees Celsius. And the change in temperature, final temperature 23.48 minus initial temperature 22.15 degrees Celsius. So delta T here ends up being 1.33 degrees Celsius. If I multiply that by 400 and that by 4.18 to three significant figures, I get that the heat transferred to the solution was 2,220 joules. So that was the heat transferred into the solution by the chemical reaction. And so what we have to remember is that this heat change occurred for the solution. In calorimetry experiments, the heat of solution is going to be the opposite of the heat of reaction, because the solution is part of the surroundings, not part of the system. The system is the chemical reaction itself. And at best, water is a participant in the sense that, yes, there is some water being made by the reaction. But the majority of the water that is in that cup was there before the reaction took place. And so we have to think about it from the big picture kind of scenario. Water isn't a reacting piece here, it's a medium. It's part of the overall surroundings that allow the reaction to occur. Just like if we did a reaction in the open atmosphere, we wouldn't think of nitrogen being the most abundant gas, as being a reaction participant, but rather part of the surrounding solution. And so if I was monitoring the temperature change of a sample of nitrogen, I wouldn't think of nitrogen as being part of the system. I would think of the air as part of the surroundings. And so it's the same idea. So that being said, if our heat of solution is 2,220 joules, and that is the opposite of the heat of reaction, then negative 220 joules would be the actual heat of reaction. Now, that's not what the question is asking. The question is asking for the enthalpy of reaction. And so we need one more piece to the puzzle here. To turn this heat of reaction into an enthalpy of reaction, this enthalpy value is on a per mole kind of basis. So what we need to do to turn our heat of reaction into an enthalpy of reaction is we need to divide by the number of moles in the reaction. And this is where, this is another one of those places where that millimole technique that we've been using really comes in handy. We can see that we've got 200 times 0.2. Well, 200 times 0.2 would be 40 millimoles of the acid, and we've got the same amount of base. And since all of this reacts in a 1-to-1 fashion, we'll end up with 40 millimoles of each product by the end of this. 40 millimoles is the same as 0.040 moles. And so now we can take that negative 2,220 joules divided by our 0.0400 moles. And that'll give us negative 55,500 joules per mole, which we could easily convert to kilojoules, negative 55.5 kilojoules per mole. And like I said before, more often than not, this is kind of the form that we use, just because the joule numbers can kind of get carried away, especially when we start talking about molar values. So this is more along the lines of the kinds of calorimetry problems that you should come to expect. Not to say that there won't be a heat transfer question out there in the ether somewhere, but if it is, it's going to be a heck of a lot simpler than that first one that we did. Most of the time with calorimetry, though, we're observing chemical reactions, not just I put a hot object into a cold object, how much heat gets transferred in the process. Any questions here? All right, let's look at another example. The specific heat of octane in the liquid phase is 2.22 joules per gram Kelvin. Now, notice here, the specific heat is given in degrees Kelvin instead of Celsius. That's completely okay. We don't actually have to change anything. We don't even have to change our temperatures into Kelvin to work it. Because since we are talking about changes in Kelvin temperature, Kelvin and Celsius are on the same scale. So me going from 0 degrees Celsius to 20 degrees Celsius, will that be from 273 to 293? The answer is 20 degrees either way. So if you see that Kelvin term in the specific heat, don't worry about it. It's the same as if it was degrees Celsius, because they're on the same scale and we're looking at the change in temperature, not the absolute temperature. If we had to do absolute temperature calculations, then yes, we would have something more considerable to do. We would have to change the temperatures from Celsius to Kelvin to do that. First question, how much heat is required to raise the temperature of 80 grams of octane from 10 to 25 degrees Celsius? So for that question, Q is equal to MC delta T. Our mass is 80.0 grams. The specific heat we were given, 2.22 joules per gram degrees Celsius. And we're going from from 10 to 25.0 degrees Celsius. So that's a temperature change of 15 degrees. 15 times 2.22 times 80 to 3 significant figures would be a positive 2,660 joules. The second question sounds kind of complicated, but it really isn't. Question is, which will require more heat? Raising the temperature of 1 mole of octane by a certain amount, or raising the temperature of 1 mole of water by the same amount? What this question is really asking is, which one has the greater heat capacity? And so how we can convert these to heat capacities is we just need to multiply the specific heat by the molar mass. So for octane, it's 2.22 joules per gram degree Celsius. Molar mass of octane, 12.01 times 8 plus 1.01 times 18. I get 114.26 grams per mole. Molar mass times 2.22 would give us, to 3 significant figures, 254 joules per mole degree Celsius. So this would be the molar heat capacity of octane instead of the per gram. For water, water has a higher per gram specific heat, but its molar mass is only 18.02. So 4.184 times 18.02 to 4 significant figures would be 75.40 joules per mole degree Celsius. So from this calculation, it's pretty obvious. The octane requires considerably more heat per mole than the water does. 254 compared to 75.4. So if you find a question like that, where it's asking you to do a direct comparison, you don't need to get too deep into specifics there. It didn't say which requires more heat, raising a mole of octane by 8 degrees versus a mole of water by 37 degrees. If you did that, you'd have to actually calculate the Q values for each and compare them. Here, we're doing an apples to apples comparison. Convert each of the masses into moles and take it from there. Any questions? Now, when it comes to calorimetry, we've seen this first type quite a bit. The constant pressure calorimeter. Constant pressure calorimeter gives us this coffee cup or this styrofoam kind of vessel that we put our stuff in. We measure the change in temperature of the solution. And since that solution is part of the surroundings, we can easily convert it as equal and opposite to the heat of reaction. And the heat of the reaction is related to the enthalpy change. All that we need to do is add that molar term to turn the heat we observe in our experiment to an enthalpy value for the reaction. There is another type of calorimeter. It's called a constant volume calorimeter. This is more of an isolated kind of system as opposed to a closed system, or closed-ish as we were calling it earlier this week, because it's almost impossible to get that calorimeter perfectly closed. There's always going to be a hole or some sort of crack for matter to get in and out of. Now, because there is variability in the pressure, we can't just simply do a heat transfer calculation like we have done for the others. We have to take into consideration that the calorimeter itself needs to be considered as part of the system. And so what we end up doing is we end up doing something called a calorimeter constant. And that calorimeter constant basically takes into account how much heat is being absorbed in the calorimeter total as opposed to just in the solution. So we get a lot more precise data out of these kinds of calculations because we're not only accounting for, okay, the water increased by a certain temperature, we've also done some calibration that says, okay, the walls of the vessel also gained heat. The vessel itself gains heat. The air above the solution gains heat. And we can wrap all of that into a singular constant rather than looking at the specific heat of an individual piece of it. And so when we do that, the heat of the reaction is equal to the opposite of that calorimeter constant multiplied by the change in temperature inside of the calorimeter. Now, in our lab, our constant pressure calorimeters look a little bit different. We don't actually have the coffee cups. We have a little bit stronger, thicker styrofoam. Doesn't come close to what a bomb calorimeter actually is able to do. For those vessels are usually made out of steel and insulated materials. And the reaction vessel itself is usually a vessel inside of the vessel that is surrounded by water. And so what we do is we measure the temperature change in the water and use that as to calibrate the calorimeter itself. All right. Give you a second here. Go ahead and start working on this one on your own. You've got all the data you need. We've done these calculations before. Let's see how you can kind of think on your feet. So the key to this problem, like I said, it's recognition of the fact that we're doing the same thing. The heat of reaction is going to be equal to the opposite of the heat of solution. And that we had to recognize that both of these factored into the mass of the solution. So Q of solution would have been equal to the mass 64.25 grams times the specific heat, 4.184 joules per gram degrees Celsius, times the change in temperature. Final temperature was 16.9. Initial temperature was 22.0. So the heat of solution, 64, change in temperature, 16.9 minus 22 is negative 5.1 degrees Celsius. Times 4.184 times 64.25 to two significant figures because of that change in temperature. We're getting a negative 1,400 joules. Since the heat of the reaction is opposite the heat of solution, that means that the heat of reaction would be a positive 1,400 joules. This should answer the second question. Second question, is this endothermic or exothermic? It's endothermic. The heat of the reaction is increasing. It's positive. Now, to turn this into a delta H value, I need the number of moles, 4.25 grams of ammonium nitrate. That's NH4NO3. Molar mass, 14.01 for nitrogen, and there are 2 of them. 1.01 for hydrogen, and there are 4 of them. 16.00 for oxygen, and there are 3 of them. 80.06 grams in 1 mole. So 4.25 divided by 80.06, 0.0531 moles. So delta H is equal to 1,400 joules divided by 0.0531 moles. To two significant figures, positive 26,000 joules, which would be the same as positive 26 kilojoules, both of those being per mole. All right, any questions with this example? All right, so just wanted to point out a couple things. We aren't going to do a whole lot with bomb calorimetry. Bomb calorimetry is kind of out of our league as far as material that we can acquire and what we can actually do with it. Like I said before, most of the calculation in it comes down to calculating what the calorimeter constant is. And we can do that by doing a simple experiment inside of the bomb calorimeter, seeing how much heat the bomb calorimeter absorbs when we do so. So calculation like this becomes possible, where if we're trying to figure out the heat capacity of the calorimeter, we can do a reaction where we know the energy released, and then we can figure out how much energy it absorbed. So remember that calorimeter constants are equivalent to energy divided by changes in temperature. Well, in this case, we have something that burns at 26.38 kilojoules of energy for every 1 gram of benzoic acid. And it just so happens that we burned exactly 1.000 grams of that benzoic acid. So our heat here would be 26.38 kilojoules. They made it nice and easy for us. Here's the heat associated with the combustion for 1 gram. Let's use exactly 1 gram. This is how much heat was generated by the reaction. And the calorimeter changed in temperature by 7.248 degrees Celsius. So 26.38 divided by 7.248 to 4 significant figures would be 3.640 kilojoules per degree Celsius. That would be the calorimeter constant. So if we were to do a future experiment inside of this calorimeter, all that we would have to do is run the reaction and see how much the temperature inside the calorimeter changed. And then we would take that temperature change, multiply it by 3.64 kilojoules per Celsius, and that would give me the amount of heat associated with whatever it is that we did, which we could then convert to delta H. Now, the most common application of this is in the food chemistry industry, when we're trying to figure out how many calories are in a substance, when we're trying to figure out nutritional information about a substance. And so again, this is mostly out of our depth, so we're not going to spend a whole lot of time talking about it. In fact, we're going to switch gears. I have a couple of slides here about it, but in the interest of our time and the relevance to our what we need to know, we're just going to kind of let those sit. If you're interested in it, your book has a whole section on deriving energy from food and doing that kind of calculation. I want to move into the last thing out of this chapter. Now, if you remember way back, got to hop way back in the Wayback Machine, back to chapter 4, when we talked about Lewis structures and we talked about bonds. We talked about at that time the trends in bond energy. Long bonds are weaker, short bonds are stronger, double bonds are stronger than single bonds, that kind of thing. Well, we can take those same bond energies that we looked at kind of globally in chapter 4, and we can use them to calculate changes in enthalpy, because we know that in order for a chemical reaction to occur, we basically have to restructure the molecules. And so if we take a look at it from the perspective of, we know to get from reactant to product, we're going to have to break some of the bonds in the reactants and form new bonds in the products. Breaking those bonds is going to require energy. That's part of what we see in activation energy. We also know that forming those new bonds will release energy as the unstable, unassociated atoms start to combine with each other, and they release their energy as they become more stable. So a way of looking at heat of reaction can be from that perspective of the bonds themselves. if I take the bond enthalpies of all those bonds that are broken, all that would be positive energy going in. And if I subtract from that all of the bond enthalpies for all of the bonds that form, that would be energy coming out as the reaction proceeds. Comparing those two, subtracting them from each other, would give me a heat of reaction. And it should be on the same par as the same kinds of things that I would get from a Hess's law, from a heat of formation, from all the other techniques that we've talked about in this chapter. It's on the same line. It's just a different way of looking at the problem. And what it allows us to do is it allows us to make these kinds of diagrams. This is called a Born-Haber diagram. Basically, it shows, okay, this is what we had at the beginning. I break the bonds. Here's my transition state. The bonds reform down here. Energy drops. I can see that there is a difference between where I started and where I ended. And that difference must be the enthalpy change. And so if the products have a lower energy than the reactants did, that's an exothermic process because energy in net was released as the reaction proceeded. And if the products happen to be higher in energy, then that would be an endothermic process because that extra energy input stayed in the bonds in some kind of way. Now, in your textbook, again, in the appendices, there is a list of average bond enthalpies. In the lecture packet, there is a similar table, and that similar table can be found on really the first actual page of that appendix table. Now, all of the bond enthalpies that you are going to see in those tables are going to be given as positive values. And they're going to be given as such because we are always looking at bond enthalpy from the perspective of breaking the bond. So, for example, just looking at the very first example on the appendix, a hydrogen to hydrogen single bond has a bond enthalpy of 436 kilojoules per mole. So if I wanted to break a hydrogen to hydrogen bond, it would take 436 kilojoules to break a mole of those bonds. But on the flip side, if I am forming a hydrogen to hydrogen single bond, the formation of that bond from the individual atoms would release the same 436 kilojoules of energy per mole. So this is a listing of bond enthalpies. This is one from an older textbook that I have. Like I said, you do have a text in your textbook that will do this. You also have what I think is a pretty convenient table. Kind of a nice little one pager here. Out of the appendices that I've given you electronically in Blackboard and at the top of Top Hat. But they do the same thing. So let's take a look at a couple of examples of how to solve these kinds of problems. So the first one here, determine the heat of reaction for the following chemical reaction. I've got two of these organic molecules that's propene reacting with 2 ammonia and 3 oxygens to make this nitrile compound and water. So when we do these kinds of things, it's often we're going to have to resort to Lewis structures to figure out what is actually changing because it's not always easy to see. So structurally, I've got a 3-carbon chain here. And on that carbon chain, I've got some hydrogens just hanging out to fill out the octets of those carbons. And I've got 2 of those. And I've got ammonia. Ammonia structure is pretty well known. It's ammonia, 3 hydrogens on the 1 nitrogen. I also have 2 of those. And I have 3 oxygens, oxygen being in the molecular phase, a double bonded molecule, and I've got 3 of those. And on the flip side, I've got this compound here, which is still a 3 carbon chain, but it's changed up a little bit. I've got a double bond on this side, and this last carbon has triple bonded to a nitrogen. And so I've got 2 of those, and I've got waters, and I've got 6 of those. So the next thing that I want to do, now that I've got my Lewis structures kind of intact here, is I want to take an inventory of all of the different types of bonds that are there. And so there's going to be some redundancy on each side of the equation, and we'll take care of that redundancy after we've taken the inventory. So I can see that in this molecule, I've got 1, 2, 3, 4, 5, 6, 7 carbon to hydrogen single bonds. And since there are 2 of them, I've got 14 in total, 14 carbon to hydrogen single bonds. I also have a pair of carbon to carbon double bonds. So I've got 2 carbon to carbon double bonds. I also have 2 carbon to carbon single bonds. And that takes care of all of the bonding in the propene. For the ammonia, I've got 3 nitrogen to hydrogen single bonds times 2. So 6 nitrogen to hydrogen single bonds. And in the oxygen, I have 1 oxygen to oxygen double bond, but there are 3 of them in total. So 3 oxygen to oxygen doubles. So that is a summary of all of the bonds on the reactant side. On the product side, I have 1, 2, 3 carbon to hydrogen single bonds times 2. So I have 6 carbon to hydrogen single bonds in this molecule. I also have a carbon to carbon double bond times 2. So 2 of those in total. A carbon to carbon single bond times 2. So 2 of those in total. And a new one here, a carbon to nitrogen triple bond. So I've got 2 of those in total as well. And for the water, I have 2 oxygen to hydrogen single bonds times 6. So a total of 12 of those. So like I said, in the inventory here, there is some redundancy. And if we do the inventory like this, the thing that we can recognize, oh, hey, that carbon to carbon double bond, it didn't break. And it didn't form. I can cancel it out. That carbon to carbon single bond didn't break, didn't form, cancel it out. Some of these carbon to hydrogen bonds changed, but 6 of them did not. So I can take away 6 of these, which would leave me with 8. And so this reaction now kind of distills down to the breaking of 8 carbon to hydrogen bonds, the breaking of 6 nitrogen to hydrogen single bonds, and the breaking of 3 oxygen to oxygen double bonds, and the formation of 2 nitrile groups and 12 hydroxyl groups. Now I can grab my bond energies and tally it up. My 8 carbon to hydrogen bonds, carbon to hydrogen single bond is 414 kilojoules. My 6 nitrogen to hydrogens, 389 each. And my 3 oxygen to oxygen double bonds, 498 each. Add that all up together. 8 times 414 plus 6 times 389 plus 3 times 498. 7,140 kilojoules. So if I ran 1 mole's equivalent of this reaction, so everything there in molar quantities, 2 moles of propene, 2 of ammonia, 3 of oxygen, it would require 7,140 kilojoules to do it. What do we get back? I get 2 nitrile groups, carbon to nitrogen triple bond is 891. And 12 hydroxyl groups, OH is 464. Two times 891 plus 12 times 464 is 7,350. So the heat of reaction is the bonds broken, 7,140, minus the bonds formed, 7,350. Which would be negative 210 kilojoules. That would be my heat of reaction for this reaction as it is written. Notice I didn't put per mole on there because none of those are singular coefficients. So that 210 kilojoule loss is per the stoichiometry of the reaction. Right, any questions about bond enthalpies? All right, let's try one ourselves. And the examples I'm going to have you do are a lot simpler than that one. Should be a lot easier to recreate the Lewis structures. So let's do these and get some participation points and call it a week. So start off with this one. the chlorine reacting with hydrogen to make hydrogen chloride. All right, let's see how we did. So this one was a good bit simpler. There were fewer molecules, and the molecules were, smaller, simpler. So on one side, you had the chlorine-chlorine single bond, chlorine-chlorine single bond has a bond enthalpy of 243 kilojoules. And you had a hydrogen to hydrogen single bond enthalpy for that is 436 kilojoules. So I put those together. Total energy to break the bonds would have been 769 kilojoules. On the product side, we had 2 hydrogen to chloride single bonds. Each one is 431 kilojoules. So the total energy released when those bonds form would have been 862 kilojoules. To get delta H, I would subtract 679 minus 862, so bonds broken minus bonds formed, and I would have got negative 183 kilojoules as my answer there. All right, any questions with this one? All right, let's try one more then. All right, so this one's a little bit more complicated. It's a little bit more complex. You're going to need to do something a little bit more closely resembling what we did in the first problem. Now, the structures themselves are pretty similar, but I will give you, let me give you the structures here for the 2 larger organics, because it's not as apparent what's happening there. So you know this molecule, this is acetic acid. We just don't usually write it out in its molecular form. And then you're also somewhat familiar with this other product. This is an ester, not far unlike the ester that we made in lab earlier this semester. It's a different ester. The one we made in lab was propyl acetate. This one is just methyl acetate. So those are the 2 organic structures. So take that and use it, and we'll come back in a couple minutes, go through this problem, and cap off the week. All right, let's see how we did. So you should have been able to finish out the last 2 Lewis structures because they were relatively simple, and do an inventory of the structures based upon those. And so if you had done that, you would have ended up with the inventory seen here. And you should have recognized also, there's actually a lot of redundancy. Not a whole lot actually changed, even though it looks like it did. All of the carbon hydrogen bonds stayed the same. Carbon to carbon stayed the same. The carbon to oxygens stayed the same. Only difference was we added one extra carbon to oxygen bond on the product side. And we exchanged a carbon to iodine bond for a hydrogen to iodine bond. So when it comes down to it, oxygen to hydrogen is 464 kilojoules. And carbon to iodine is 238. Add those together. We get 702 kilojoules. So that's our stuff on the reactant side. And on the product side, we've got carbon to oxygen single bond, that's 351. Hydrogen iodine, 297. Add those together. $351 plus 297 is 648 kilojoules. So put it all together, delta H, bonds broken, 702 kilojoules, minus bonds formed, 648. And we get 54, positive 54 kilojoules. So I would tell you the same thing that I've told you before. Table values vary from reference to reference. So use the values associated with whatever assignment is that you're doing. So if it's in smart work, use the appendices in the textbook rather than any of this stuff. The reason I pulled this out here out of the lecture packet mainly because it was convenient to me. And also you'll be given this kind of information for the quiz when that day comes. To look up the information there. So I'm not surprised that there are differences and discrepancies. It's the technique of the calculation that I'm more concerned with evaluating. So that's all for this day and for this chapter. Does anybody have any questions?